This is Crew Dragon, and when it potentially goes for a flyby around the moon, well, that's Orion, but in any cases, it usually goes through something called free return trajectory. Have you ever wondered how Apollo 13 came back to Earth even though it suffered a severe rupture of oxygen tank number 2? It all comes down to the orbital mechanics and surrounding physics laws that govern the trajectory of the spacecraft. Today, I am more than happy to introduce the Apollo 13's free return trajectory from the moon that helped astronauts safely come back to Earth. Before we actually get down to calculating the actual trajectory of Apollo 13, we have to learn something called vis-viva equation. Since we haven't learned this in grade 12 curriculum, let's derive it using the gravitational potential energy equation. First, let's explore the definition of epsilon in the context of orbital mechanics. You guys would know that the total energy equals to kinetic energy plus potential energy, which is 1/2 mv squared minus gmm over r. Epsilon basically being energy total divided by the mass of the object is basically neglecting the object's mass, and the equation is 1/2 v squared minus gm over r. M in this case being the Earth's mass. In any orbits, epsilon 1 equals to epsilon 2 for two locations in the same orbit. This is basically another word for saying the energy is perfectly conserved, but epsilon is just energy without the object's mass. We can group the kinetic energy part together as well as the potential energy. We can rearrange it so that the potential energy side becomes Gm, bracket open, 1/r1 minus 1/r2. And from here we can apply the Kepler's second law we learned in the Earth and Space unit. And Kepler's second law basically defines that when you're closer to the Earth, given you're a satellite, the time you're gonna spend to orbit the same amount, in this case the area of the triangle, the time it takes significantly shorter than when you're in the higher altitude. The highest point in the orbit in an elliptical orbit is called the apogee, and the lowest point is called the periapsis. So applying the Kepler's second law, which is R1 V1 equals to R2 V2, we can easily tell that V2 equals to R1 V1 over R2. And this we can substitute into V2. And this, if we rearrange, we get V1 squared equals to Gm bracket R2 minus R1 over R1 R2 times 2R2 squared minus R2 squared over R2 squared minus R1 squared. And if you use the differences of squares, we can get Gm 1/r1 times 2R2 over R1 plus R2. And from this, we get this legendary equation. V1 equals to square root of 2gm R2 over R1 bracket R1 plus R2. And this is the velocity required at periapsis, the lowest point in the orbit, to produce a Hohmann transfer orbit to the desired altitude. And you might ask, what is Hohmann transfer orbit? Well, it's typically used in interplanetary missions, or when we're just simply going to the moon, or when we change, or when, for example, the International Space Station is trying to change its altitude, perhaps to avoid a debris. When you accelerate at the lowest point of the orbit, the altitude at the highest point of the orbit is going to increase, which can make a circular orbit into a elliptical orbit. And when the apogee, which is again the highest point in the orbit, is high enough so that it intercepts with the gravitational field of the moon, that's how you can basically shoot a spacecraft so that it's going to be attracted to moon's gravity which is in another terms called a moon flyby. Normally in Apollo missions you would decelerate so that it's slow enough to be captured by moon's gravitational field, but in case of Apollo 13, again, it's a free return trajectory, so it just flew by the moon and then it bounced back to the Earth's gravitational field. There's another equation that we learned that has to be applied in order to get our final delta V equation, which is circular orbital velocity equation. V equals the square root of gm over r. This is derived by Newton's second law. You guys should know F equals to ma, and the universal gravitational law, which is Fg equals to gmm over r squared. Don't confuse it with the potential energy, which is negative gmm over r. But if you actually apply this to our equation, which is V1 equals to square root 2gm r2 over r1 plus r2, we can combine this and the orbital velocity equation into calculating delta V, which is V2 minus V1. In this case, we're just gonna say V1 minus V, and we're treating V1 like V2. And we're basically transferring from a circular orbit to a elliptical orbit that's gonna intercept with moon's gravitational field. So we can say delta V equals to square root of 2gm r2 over r1 plus r2, which is the elliptical orbit, minus square root of gm over r. Notice that the orbital velocity equation can only be applied to circular orbits. It cannot be applied to elliptical orbits. So we're basically subtracting those, and we get delta V equals to square root of gm over r1 bracket square root of 2r2 over r1 plus r2, and the entire thing minus 1. And this is an equation to calculate the delta V required for the first burn of any Hohmann transfer. So when Saturn V, which carried the Apollo spacecraft, launched, it separated its first stage, and when the second stage, the third stage, known as SIVB, it basically burned through a couple tons of fuel in order to get the necessary velocity to get to the moon. Now, we're gonna look at a real-life example that actually involves a spacecraft going from a lower altitude to a higher altitude. First, let's recall the equation that we just learned. Delta V equals the square root of gmr1 bracket square root of 2r2 over r1 plus r2 minus 1. If we plug in the numbers in our equation, but to get the r1 and r2 values correctly, we have to add the Earth's radius value to the altitude value, because the r value is supposed to be calculated from Earth's center to where the object is. So in this case, the altitude itself is calculated from the Earth's surface to wherever the object is in the space. But we have to basically account for that distance between the surface and Earth's center. So that's what we're going to do. So if we add them up, we get an R1 value of 654.0609 meters. We just converted kilometers to meters as well. And we get an R2 value of 665.3730 meters. Finally, if we plug all the values in, we get a delta V of 33.38193 meter per second for a Hohmann transfer to reach 222.73 kilometers. The lowest point in the orbit's gonna be 169.609 kilometers, but the highest point in the orbit is going to be 282.73 kilometers after a burn that involves a velocity change of 33.38193 meter per second. Yes, we did go from a circular orbit to elliptical orbit that does touch upon the 270 kilometers point. But what if we want to make a circular orbit that constantly stays at 270 kilometers instead of shifting between 270 kilometers and around 100 kilometers? Well, we can use a new equation, but this equation is very related to the equation we just used. The delta V equation that basically involves going from a circular orbit to elliptical orbit that is of higher altitude. If you look at the original equation, we can notice that we are subtracting a orbital velocity equation, in this case the circular orbit velocity equation, from the elliptical orbital velocity equation. But if we get to reverse it, and if we put the circular orbit velocity equation first, then we can say we're going from an elliptical orbit to a circular orbit instead of elliptical orbit instead of a circular orbit going to an elliptical orbit. So we're reversing the order, and we get a new equation like this: delta V equals to square root of GM over R2 bracket 1 minus square root of 2R1 over R1 plus R2. So now that we got a new equation, we can plug in the numbers that we got from our measurements. And we can get a new delta V of 33.2391 meter per second. So if you were to talk about the total delta V that is needed to go from a 100 kilometer circular orbit to a around 200 kilometer circular orbit, we need a total delta V of 33.38193 plus 33.239 equals to 66.621 meter per second. If you check the official NASA data, it seems that the numbers are looking good. So that was it. That's how you calculate the delta V of a Hohmann transfer plus circularization burn. So thanks for watching.